So it's a great pleasure to have Lenny Ng with us today. And the title of this talk is New Invariants of Legendrian Links.
Thanks very much to the organizers for the invitation to speak here and the opportunity to talk to people across all sorts of time zones. I think this seminar is it's a really important service to the community, so I'm really happy that it's persisted past the worst of the pandemic. The only issue for me is that I'm pretty out of practice giving Zoom talks, so we'll see how this goes. Hopefully there won't be any terrible technical glitches. I once gave a talk, and at some point my laptop froze, and so there was about 5 minutes of just blank air when nothing was happening, and that was a little bit embarrassing. But hopefully that won't happen here. But nevertheless, so the usual. Please do interrupt if you have questions. I do have a second screen, so I think in theory I might be able to see things in the chat, but I'm also happy just to be interrupted anytime. Okay. And the slides. So the slides for the talk that I'm giving right now, there's a URL down here for it. And I guess also you all, the organizers, you post this on the seminar webpage. Is that correct? The slides.
Correct.
Yeah.
Yes.
Yeah. Great. So that's also possible. Okay. Great. All right. So the story I want to tell you about today, it's going to start with a very well-established Floer-theoretic invariant in contact topology. And the idea is to upgrade this to new and hopefully more powerful, more interesting invariants by exploiting connections to or importing ideas from a different area of mathematics that's maybe a little bit less familiar to those of us in symplectic topology. So what's the invariant I want to start with? I want to start with Legendrian contact homology. So this is associated to, in the setting I'm going to be using, associated to Legendrian knots and links in 3 dimensions. And the area that I want to import ideas from is cluster theory, sort of maybe algebraic combinatorics-ish. Maybe a little bit also from microlocal sheaf theory, but for today, mainly from cluster theory. But the way that I'm going to set up this talk, I actually won't be talking about, it won't mention the word cluster for a very long time. So really, you can just think of it as being some sort of motivation for what I'm going to be talking about. But at least the first bit of the talk will be just sort of purely in symplectic topology and stuff that we could have done a while ago, I guess. Okay, great. Let's see. So it's going to take me a second to get the hang of this. Okay, so today I'm going to stick to a really simple setting, and this is going to be just a standard contact 3 space. So this is R3 equipped with a standard contact structure. So for me, the standard contact structure is the kernel of the standard contact 1 form, which is I like dz minus y dx. So there it is. Okay, so a link inside of this. So by link, I mean knot or link. Whenever I say link, that it could be just a single component knot. So a link sitting inside of here is called Legendrian if it's everywhere tangent to this standard contact structure. So that just means that the standard contact 1 form, if you pull it back to this link, it's identically equal to 0. So here's an example that I'm going to be pulling through the talk. This is the trefoil. So what I've drawn is what's called its front projection here. And the front projection is the projection into the XZ plane. This is just a sort of a nice way to picture these things. The point is that if you draw the projection of a Legendrian link into the XZ plane, then you can always recover the y coordinates so since dz minus y dx is everywhere 0, then y has to be dz dx. So you can recover the missing y coordinates by the slope of the front projection in the XZ plane. And so this has several sort of interesting features. So one of them is that wherever you have a double point in this projection, you don't actually have to specify which is the overcrossing and which is the undercrossing. I'll circle this. I have specified which one is over and which one is under, but the point is that the strand with more negative slope is always going to lie above the strand with more positive slope because the y direction points into the screen. Okay. Okay, so that's one feature. And the other feature that's sort of unusual from the point of view of smooth knot theory is that we have these cusps. So the left cusps and right cusps. And that's just because there can't be any vertical tangency, since again, y is dz dx, and that would mean that y is infinity at that point. So instead we have these semi-cubical cusps where the Legendrian can change directions in the x coordinate. Okay. All right, so that's a right-handed trefoil, what I've drawn there. And again, this is something that I'll just be using as a running example as we go. So this is R3 with a standard context structure. There is an associated symplectic manifolds to this, which is the symplectization. So I think this is pretty familiar to a lot of people. So what we do is we just take the contact manifold and we cross with R. And I'm going to, the T there is, that's the coordinate in the R direction. So my coordinates in R cross R3 are going to be X, Y, Z, and T. And the symplectic form on this is just d of e to the t times the standard contact 1 form. Okay. Okay, so I've attempted to draw a picture of this over here. So R3 is horizontal and the R direction is vertical. And then it's an easy observation to say that if you have a Legendrian link inside of R3, so what I've written as lambda, then if you take the cylinder over this, so R cross lambda, I guess this could be a collection of cylinders if lambda is a link, then you get something that's Lagrangian sitting inside of the symplectization. Okay, so it's the correct dimension and the standard this symplectic form vanishes along the cylinder. Okay, so that follows just from the fact that lambda is Legendrian. Great. So we can actually extend this picture of starting with a Legendrian having this Lagrangian cylinder to a slightly fancier setup. And so I'm going to write this. This is actually just sort of motivation. So let's see. So I'm going to think of some sort of category that you can build out of these Legendrian links. So again, this isn't strictly necessary for what we're doing, but sort of a nice picture to keep in mind. So the objects of this category are oriented Legendrian links inside of R3. And so morphisms, so the Lagrangian cylinder that I mentioned before, so that's going to be an identity morphism from a Legendrian link to itself. And more generally, we have this notion of an exact Lagrangian cobordism. So this is what's on this slide here. So an exact Lagrangian cobordism is a Lagrangian sitting inside of the symplectization, which for near sort of plus infinity in the t direction, it looks like a cylinder over one Legendrian lambda plus, one Legendrian link lambda plus, and at near minus infinity in the r direction, it looks like a Lagrangian cylinder over lambda minus. So that's these two conditions here. And then in the middle, it can be anything, as long as it is, well, it can't be anything. It has to satisfy something, and the something is the second condition here. So the second condition is exactness. And what this says is that, so remember that in the symplectization, the symplectic form is itself exact. So it has a primitive, which is e to the t times the standard contact 1 form. And so the statement is that the condition is that this 1 form, when you restrict to this L, this surface L actually has to be exact itself. So it has to be d of some function that's valued on it. That goes from L to R. And then there's another condition that's sort of a technical condition that it needs to be constant at the ends, which only comes into play if there are multiple components of one or both of the ends. So this exactness condition immediately implies that L is Lagrangian, since so this primitive of the symplectic form is itself exact. So when you take d of it, you get 0. Okay. Okay, so you can think of these as this sort of a cobordism as a morphism. This always makes my head hurt because I think of things as going from top to bottom, but this is probably not good. So I think I'm trying to switch over. So think of this as a morphism from lambda minus to lambda plus. The lambda minus is down at the bottom, lambda plus is up at the top. And you can compose these sorts of morphisms by just taking one of these exact Lagrangian cobordisms and removing the two infinite ends and then just concatenating. So if you remove these two infinite ends, so you just have this portion in here, that sort of, it has two boundaries. One is lambda minus on the bottom and one is lambda plus on the top. Then you can imagine if you have three Legendrians and you have morphisms between them, pairs of them, then you can concatenate them to get a morphism, which is the composition. Okay. And for later, for future reference, so there's one specific type of exact Lagrangian cobordism that I'm going to be particularly interested in, and this is a filling. So a filling is just a cobordism where the bottom end is just empty. So there's something on the top, but there's nothing on the bottom. So this is my cartoon picture of that. Okay, great. I've put together this geometric picture because it's going to come in handy in a second, but first I want to step back and talk about Legendrian contact homology. So this Floer theoretic invariant. And here is my very brief introduction to Legendrian contact homology. So this was something that I think is about 25 years old, might be slightly older. And what it does is that it associates to a Legendrian link. So again, our setting is just inside of R3, although this works more generally. And we're going to associate to this what's called the Chekhanov-Eliashberg differential graded algebra. The formulation that we normally use now is due to Chekhanov, but Eliashberg had sort of laid out the idea at more or less the same time or slightly earlier. You don't need to know too much about this, except, so I've tried to indicate how this goes, but so let me just go through the highlights. So this has two parts. So the algebra for me in this talk is going to be a polynomial ring over a field K, and it's generated by what are called the Rabe chords of lambda. So those are just Rabe flow lines flow lines of the Rabe vector field that begin and end on the Legendrian. I don't need to get more into this right now. This is actually an oversimplification. So you have to include some more generators corresponding to base points on the Legendrian link, but I'm going to ignore those. So that's the algebra. So just think of it as like a polynomial ring. There's some grading that I haven't told you about. The differential, sorry. So the differential counts holomorphic disks. And these are holomorphic disks in the symplectization, so in R cross R3, and they're going to have boundary on the Lagrangian cylinder over lambda. So that's R cross lambda. That's this purple thing that I've drawn here. And there are boundary punctures on the source disk. So I've tried to indicate those here. And those boundary punctures are going to map to asymptotically to Rabe chords of the Legendrian lambda at plus or minus infinity. So one of them is going to go to, this one is going to map to a strip. So this is a strip over a Rabe chord at plus infinity. It's asymptotic to this Rabe chord that I'm calling AI. And then these other ones here are mapping asymptotically to things down at minus infinity. This has become a little bit too crowded, so let me get rid of that. Okay. So I'm going to use the terminology of punctures. So this sort of holomorphic disk has one positive puncture. Oh, I haven't told you about the almost complex structure, but anyway, there's some standard way to choose an almost complex structure on the symplectization, and then these are J holomorphic with respect to that. Okay, so where was I? Right, so to define the differential, you count these holomorphic disks with one positive puncture, so that's, in this case, this is what I've written as AI, and any number of negative punctures. It might actually be 0, but it's at least 0. And to any such holomorphic disk, we look at only rigid moduli spaces of such things. So this is some sort of standard Floer theory type construction. And then to any rigid moduli space, so one of these holomorphic disks, this contributes to the differential of AI, which is the positive end. And what it contributes is it contributes the word, which is just the product of the Rabe chords at the negative end. So that's, in this case, I've written it as AJ1 through AJK. And there's maybe some sign associated to this moduli space. So that's what I've written as this number here. Also, if there's more than one, I mean, this is counting the number of points in this rigid moduli space, but with sign. Okay, so in the example that I've been carrying around, this is the trefoil. There's a one-to-one correspondence, or there can be. You can set things up so that there's a one-to-one correspondence between Rabe chords of the Legendrian and crossings and right cusps for the front projection. So here you see that there are 3 crossings, 1, 2, 3, and 2 right cusps. And an example of the differential is the differential of A4 is 1 plus A1 plus A3 plus A1, A2, A3. So each of those things corresponds to some holomorphic disk with boundary on the Lagrangian cylinder. So let me see if I can just draw one of them. So A1 in this picture, so I'm not going to explain this, but I'll just draw it for you. Whoops. Oh, that's actually not so bad. So there's some sort of disk that in this picture looks like this. That's A1. Sorry, that disappeared pretty fast. So it has a corner at A4 and it has a corner at A1. The A1, A2, A3 is sort of interesting. So this one goes like this instead. So it has corners at A1, A2, and A3. So I think a number of you are familiar with this, and if not, I'm just going to let it sort of sit there.
Lenny, there's a question in the chat.
Great.
Can read it.
And indeed, I did not see it. This is thanks, Dini. Yeah, so this is a version where the Rabe chords commute, and also if we had homology coefficients, those would also commute with everything. It turns out, so in the standard formulation, you take the tensor algebra instead of this polynomial ring, so things don't commute. But in fact, for my purposes, I'm going to be forced at some point to pass to this commutative quotient. So I'm just doing it right away. So yeah, great. Thanks. Okay, so the general results of standard Floer theory arguments tells you that d squared is 0. And then you can take the homology of this differential graded algebra, and this is called the Legendrian contact homology of lambda. Okay. Great. So that is a completely insufficient introduction to the construction. Let me then move on to some properties of this thing. So one property is invariance. So this is originally due to Chekhanov with V2 coefficients, and then it was sort of boosted to other settings. There was a paper of Janet Nair and Jacques Sabeloff and myself, but really, I should actually strike that out and just say that. I'll attribute this to Chekhanov. So the statement is that if you have 2 Legendrians links inside of R3 and they are Legendrian isotopic, which just means that there is an isotopy between them of Legendrian links, embedded Legendrian links, then they have isomorphic Legendrian contact homologies. So this is an invariant under Legendrian isotopy. There's actually a stronger statement. There's some notion due to Chekhanov of a stable tame isomorphism, which is some equivalence relation between these sorts of differential graded algebras, and that in particular implies that these DG algebras are chain homotopy equivalent, and then that means that they have isomorphic homologies. Okay, so that's invariance. So since I mentioned this sort of category that you build out of Legendrian links, where morphisms are exact Lagrangian cobordisms, a nice feature of this invariant is that it's functorial. So this is something that was sort of laid out schematically by Eliashberg, Giventhal, and Hofer when they were first coming up with symplectic field theory. But the exact result that I'm going to cite is due to Ekholm, Honda, and Kalman. And this just says that, yeah, indeed. So if you have a morphism between two Legendrian lengths, lambda minus and lambda plus, and the morphism is this exact Lagrangian cobordism, then you get a map between the Chekhov-Eliashberg differential graded algebras, and it goes from top to bottom. This is why I always think of things as going from top to bottom, even though it's not great. You get some sort of cobordism map like this, and it's in fact invariant in whatever the correct notion of invariance is under Hamiltonian isotopy. So invariance in this case means up to chain homotopy or something like that. And this map also counts holomorphic disks with one positive puncture. Let me see it. Should I try to draw it? So also count. This is what happens when I try to draw it. It will also count holomorphic disks with one positive puncture and some number of negative ends, but now just in this cobordism instead of in the Lagrangian cylinder that I had before. Okay. Great. Okay. So that's Legendrian contact topology and a little bit about its properties. So now what I want to do is I want to talk about how we can try to upgrade Legendrian contact topology. And one way to do this was already sketched out by Eliashberg, Giffenthal, and Hofer, again, when they were talking about symplectic field theory and sort of laying out this idea of how to use holomorphic curves to study various symplectic objects. So I'm going to talk about what's called rational symplectic field theory. This is going to be very, very brief, in fact. So the idea is that Legendrian contact topology, the way that I've described it, is just the first level of some sort of multi-level invariant that in my setting would be associated to a Legendrian link inside of R3. And so what makes it the first level is it only counts holomorphic disks with one positive puncture. So you could try to count holomorphic disks with multiple positive punctures instead. And so the next level in this building would be to consider what's called rational symplectic field theory. So this is still counting holomorphic disks, but now with any number of positive punctures. So here is one that I've drawn with 2 positive punctures and 2 negative. So you could try to be fancier than this and look at other holomorphic curves of maybe multiple boundary components, maybe arbitrary genus, that sort of thing. So that's not what I'm sort of doing only the minimal possible thing that I can do once I get beyond Legendrian contact topology. So that this is I claim what that is. And for those of you who have thought about this, you know that there's like some serious issue with doing this that doesn't show up in Legendrian contact topology, and that has to do with what's called boundary degeneration. So this is if you have if you're trying to emulate Legendrian contact topology and trying to prove the analog of d squared equals 0, so you look at some one-dimensional moduli space of holomorphic disks and see how it degenerates. And the problem is that in this case, there can be this bad degeneration that couldn't happen before, and when you have a single holomorphic disk, one parameter family of these things, and then at some point it degenerates into 2 holomorphic disks that intersect on their boundaries, something like this. Okay, so this is a problem that various people grappled with for a while, and so notably Tobias Ekholm came up with a way to deal with this for multi-component Legendrians. So it's basically using multi-components and keeping track of components to just get rid of this boundary degeneration. In the specific setting of one-dimensional Legendrian knots, I also wrote some paper called Rational Symplectic Field Theory for Legendrian knots, and that was in 2008. And that dealt with this in a slightly different way, which was to use some ideas from string topology, which were in the air at the time. So this is Silibak and Latchev were promoting this a lot, but I just wanted to mention also there was some very related work of Cornea and Lalonde about cluster homology, where cluster, I guess, means something different from what I'm going to talk about today. Okay. So I'm not going to go into this more in more detail because it's a little bit complicated. And in fact, so the algebraic setup, at least in the version that I had for rational symplectic field theory for Legendrian knots, is fairly complicated. It involves some sort of curved DG algebra, and So anyway, it was reasonably complicated, and so it's a little bit hard to work with. And one thing that I sort of realized all the way back then, but didn't actually work out until last year, was that you could repackage the same information that goes into rational symplectic field theory into something that at least seems a little bit more user-friendly. Well, you may disagree with me, but we'll see. Once I get to the next slide. So instead of constructing a new invariance, which is this curved DG algebra, so I'm going to think of rational symplectic field theory as giving some sort of additional structure on Legendrian contact homology. And that additional structure is an L-infinity structure. Let's see, make this a bit bigger. Oh, no, that was too big. Come on. Okay. So this is something that I realized when I was writing up my this paper last year. I had actually promised in the introduction to my paper from 2008. So it only took 15 years to actually write up. It wasn't actually technically difficult. I just sort of didn't have the motivation to do it. And now I do. So the result is going to be that we can extend the structure of the Chekhov-Eliashberg differential graded algebra that gives us Legendrian contact homology, and we can extend it to an L-infinity algebra. And so I think that L-infinity algebras. So a lot of people are probably familiar with A-infinity algebras. L-infinity may be slightly less familiar, but it's really more or less the same thing as A-infinity algebras, except that all of the operations are now supposed to be graded symmetric. So the way to think of this is the analogy is L-infinity algebras are to A-infinity algebras as Lie algebras are to associative algebras. And so to make this more precise, so an L-infinity algebra, so what's going to happen is that we have A lambda, and we're going to give it a sequence of operations, which are just multilinear maps with some number of inputs and one output. So, and that number of inputs, it starts at 1 and then goes up. So the map L1 that takes one input and has one output, that's just going to be the original differential. So that's the differential on the DG algebra. But then the higher maps will need to be compatible in some way. And in general, the entire setup of all of these maps, they need to be compatible in the sense that they have to satisfy what are called the L-infinity relations. And again, these are the analog of the A-infinity relations for A-infinity algebras, except that you have to deal with the fact that now things are symmetric. So anyway, the first one here is just that L1 squared is 0. So that's your standard statement that L1 is a differential. The second one is compatibility between L1 and L2. And this just says that L1 is a derivation with respect to L2. I've put plus or minus. I mean, everything is graded, so we can figure out what the signs are, but it's sort of annoying. So I'm just putting plus or minus here. The third relation now involves L1, L2, and L3. So now you have 3 inputs, and there are various ways to use L1, L2, and L3 to get one output out of it. And so here are several ways to do this, and then so the sum of these things, basically mod 2, needs to be equal to 0. So if you look at this, if L3 is if L3 is equal to 0, then this entire last row here disappears. And what you get is actually just that L2 satisfies the Jacobi identity. So it's really, you can think of it as a Lie bracket. So if L3 is equal to 0, then L1 and L2 give this L-infinity algebra the structure of a DG Lie algebra. But if L3 is non-zero, then what this is saying is that L2 is no longer a Lie bracket, but it only satisfies the Jacobi identity up to some correction terms. Okay. So NLab assures me that L infinity algebras have other names. So one of them is a strong homotopy Lie algebra. And in fact, we have something that turns out to be even stronger than that. It's what's called a homotopy Poisson algebra. And the reason is that the underlying space A lambda already has a multiplication on it. It has this associative multiplication from the fact that in this case, it's just a polynomial ring. And all of these operations, L1, L2, et cetera, they all satisfy the whatever the notion is of the Leibniz rule with respect to this associative multiplication. So that gives the structure of what's called a homotopy Poisson algebra. But really, to me, the important stuff. Oh no, sorry. Yes, a homotopy Poisson algebra. And let me further say that if L3 is equal to 0, so again, this last bit here vanishes, then you can think of this as a DG Poisson algebra. So L1 would be a differential, and then L2 is a Poisson bracket in that case. Okay, so this is just in general, maybe L2 is again not a Poisson bracket because it doesn't satisfy Jacobi, but only up to these higher homotopies. Okay, great. So that's the theorem, and so let me say how we prove this, or what's the construction. So this is sort of an existence statement. So I want to say a couple words about how you construct this. And the way that you construct this is just by counting these same disks that show up in rational symplectic field theory. So this one on the left here, this is just a reminder of something that shows up in the differential in Legendrian contact homology. So this sort of holomorphic disk contributes a term A3 times A4. So those are the two negative ends of that disk to L1 of A1. So the L1 is just the usual LCH differential. But now if we have sort of more exotic disks, so here's a disk with two positive ends, then this contributes, so again, it contributes the product of the negative ends, so that's A3 times A4, so that's something inside of this polynomial ring, but now it contributes this to L2 of A1 and A2, which is up to sign also L2 of A2 and A1. Okay. So that seems pretty simple. There are a lot of the devil is in the details here. So again, you have this issue with boundary degenerations. And again, so what my strategy was is to add string topology correction terms, in this case to L2, sort of as in when I was sketching out a version of rational symplectic field theory for Legendrian knots. That's actually not so bad, but something that is worth, actually, let me go back up to the previous slide for a second. So I actually wanted this to be true for links and not just knots, because I wanted it to be well behaved with respect to cobordisms. And extending this whole theory to links turned out to be an enormous pain. So that's what I've written here. And an enormous pain in ways that were sort of surprising to me. So one of them was that if you just stick to the knot case, you actually don't have to allow the Rabe chords to commute. So it looks like you get something that is stronger. But as soon as you want to extend that to the link case, suddenly it is forced on you that the Rabe chords have to commute with each other. And it's even worse than that. It's what's forced on you, or at least what was forced on me when I was doing this, was that these string topology correction terms in the linked case actually sometimes come with, you have to count them with coefficients of 1/2, of multiples of 1/2. So you actually need to work, I didn't write this down, sorry. So it needs K to have characteristic, this is really bad. Let me just write something. So it needs K to have characteristic not equal to 2, because we actually have to divide by halves everywhere. So this has the unfortunate circumstance also that we, in a lot of this subject, it's nice to be able to work mod 2, so you don't have to worry about signs, and that is just completely not possible here. So it's, there's a lot of sort of annoying bookkeeping of signs. Okay. Anyway, so that's this is all to say, this is my explanation for why it took 15 years between when I claimed I was going to write this up and when it actually got written up. So there's a bunch of annoying details to have to deal with. Okay, so that's so far again that's an existence result. It just says that there is an L infinity algebra. So you can take your Chekhov-Eliashberg differential graded algebra, and so the differential on there then extends to this whole suite of L infinity operations. And then, so what you can prove then is that there's some sort of invariance result for this L infinity algebra. So invariance under Legendrian isotopy of the Legendrian link. And what I would like to say is that there's some sort of natural notion of L infinity equivalence between L infinity algebras. And what I would like to say is that this L infinity algebra is actually invariant under that. I wasn't actually able to prove that, so this is actually still an open question. But what I was able to do is prove that it's partially invariant. So what partially invariant means is that at least up through L2, this is invariant. Now, I'll point out that we already knew that it was invariant through L1. That's just the invariant statement for the original Legendrian contact homology. So maybe this doesn't seem like so much better, but it will give us some nice results on the next slide. So anyway, that's just I think that it's invariant just completely, but it became sort of annoying to prove, and then so I ended up only proving it through L2. Okay, so down at the bottom here, I've written down a vague conjecture.
May I say a word? What are the difficulties?
What are the difficulties? Oh, in proving invariance?
Yes.
So right. So there are I think two different ways that one could try to approach invariance, and one of them is to actually try to figure out the correct way somehow is the geometric way. So just try to figure out if you have an isotopy, so you stretch that out to some sort of Lagrangian cylinder, and then try to use functoriality, or it's sort of how these holomorphic disks break when you have these sorts of cobordisms. So this would be some sort of like version of functoriality for rational symplectic field theory that would extend this Honda-Kalman work for Legendrian contact homology. But I at least have not done the analysis to work all of this through, and so there's actually some sort of analytic work that's missing to try to do some sort of correct geometric way to do this. The sort of incorrect way to do this, and the way that I actually ended up using, is just to check that it's invariant under the various Legendrian Reidemeister moves. So this is sort of a la Chekhanov's original work. And that just becomes sort of a big mess when checking Reidemeister 2. And so that I tried for a while to show that the entire thing was invariant just combinatorially, and then at some point just gave up and decided through L2 was enough. But that's an excellent question. I don't know if that was a reasonable answer or not.
Yes, thank you very much.
Okay, thanks, Lenny. Okay, so I do think that this invariant is actually fully invariant, in which case I think it should give some sort of fairly nice invariant associated to Legendrian links that you can think of as some sort of upgrade of Legendrian contact homology. Though I have to admit, I haven't actually done that many computations yet. And another part of the conjecture is that this ought to be functorial under exact Lagrangian cobordisms. So just like for Legendrian contact homology. And actually, I have a student that's working on this right now. It seems in examples that this is functorial, and this would be pretty nice, but we don't actually have it yet. Okay. But what do we get out of this? In the meantime, even with these conjectures hanging out in the air. So firstly, I'm just going to repeat that theorem from the previous slide because the slide is now gone. So this L infinity algebra is partially invariant. Okay, so that was what I already wrote. So just knowing that it's invariant through L2 is enough to say that we have the structure of a Poisson algebra on the Legendrian contact homology. So that's not invariant. So this is just for any L infinity algebra, L2 induces a Lie bracket, which in this case is a Poisson bracket, on the homology with respect to L1. So that's this first statement here is that we get the structure of a Poisson algebra on the Legendrian contact homology, I guess the graded Poisson algebra. But the invariance result tells us that this Poisson algebra is actually invariant. Okay. So we don't need to, if we're passing to homology, then all of the higher homotopy operations just go away. Okay. So here's an example that I wanted to advertise, and this is going to be sort of key going forward for the rest of my talk. So the example is there's a family of Legendrian links called rainbow closures of positive braids. So the idea is that you start with a positive braid, which I've drawn sort of horizontally in this box here. And then you can close this up to a Legendrian link by doing the sort of thing that looks a little bit like a rainbow in the front projection. So this is the XZ projection. So the trefoil that I gave before was the case where the braid has 2 strands and it has 3 crossings. So it's like sigma 1 cubed. Okay, so anyway, there's a family of Legendrian links that are just called rainbow closures of positive braids, and this is something that we understand fairly well in various circumstances. But for us, the key observation is that you can show that in this case, all of these higher L infinity operations beyond L2, they're all equal to 0. So I think in the literature, this is that the L infinity algebra is strict. And what you get out of this is actually that then you get a slightly nicer result than just that you get the Legendrian contact homology has a Poisson structure, but actually that you have, even before you pass to homology, you already have a Poisson structure. So here you take what it is actually is it's the polynomial ring that's generated by A1 through AN, but what A1 through AN in this case are their crossings of the braid. It's actually the braid times a positive twist, so there's a bunch of extra crossings. So what this construction that I've laid out gives you in this case is a Poisson structure on a polynomial ring that's associated to any positive braids. And there's a particular family of positive braids, which I've tried to draw here. So this gives you their rainbow closures look like 2n torus length. And you get, if you compute what this Poisson bracket is in this case, you get something that actually is known in the literature. This is called the Flashka-Newell bracket. It was not known to me, but it was known to some of my collaborators. And this is some area that I actually know nothing about. Is it's sort of Poisson brackets on polynomial rings, and so I have no idea if this is like an interesting family of Poisson brackets in general that are associated to these positive braids. So I'll just leave that question hanging there. Okay. Okay, so I have, I think, about 15, 16 more minutes. So what I want to do is twofold. So one is I want to talk about some geometric interpretation for this Poisson bracket that I've written out here. Maybe interpretation is the wrong word. A geometric reformulation of the Poisson brackets. And so that's going to get into talking about fillings, which I had mentioned way back when. And then I want to talk about how this is related to cluster theory. So let's see how this goes. Okay, so what I want to do is remind you. So I mentioned before that there's this special example of an exact Lagrangian cobordism called a filling, and that's just something where there's a positive end, but there's no negative end. And in this case, the cobordism map of Ekholm-Honda-Kalman gives you a map from the DG algebra of lambda on the top to the DG algebra of the empty set. But the DG algebra of the empty set has no Rabe chords. And so what you end up with is you just get a map to the base fields, which I'm calling K. Okay, and the differential there is 0. So this DG algebra map is what's called an augmentation. It's just a map of DG algebras from the one for lambda over to the one for the empty set. And sort of more classically, maybe think of this as a map epsilon from a lambda to k, so that when you compose it with the differential in a lambda, you get 0. Okay. So it turns out that actually you can improve this by being a little bit more careful about coefficients and in particular of boundaries, keeping track of boundaries of holomorphic disks and homology classes of them. And what you get is what I've written here. And this is that actually, instead of saying that to a filling you get an augmentation, it's actually the case that to a filling you get a whole family of augmentations. Or maybe the correct way to say it is that if you have a filling and a rank 1 local system on it, which you can just think of as a homomorphism from the homology to the group of the abelian group of units in the field with multiplication, then you actually get an augmentation. So this is, I'm not explaining this, but you know, just by being a little bit more careful, you can get a whole family of augmentations associated to a filling. Okay, so how do we interpret this? So I want to define this thing called the augmentation variety. So the augmentation variety of a Legendrian lambda, this is independent of any fillings or anything. This is just the space. This is some sort of algebraic thing, which is just the space of augmentations of lambda. There you have to mod out by some sort of notion of equivalence. There's some notion of DGA homotopy that I don't want to get into. So I've just sequestered it over there in purple. And then the statement that a filling equipped with a rank 1 local system gives an augmentation tells us that a filling gives us a chart inside of the augmentation variety, which is to say that a rank 1 local system is then a point inside of this space here. And so to a point inside of there, you get some augmentation. And so you get a map from this algebraic torus over to the augmentation variety, and it turns out that it's actually injective. So this is a result of Gao and Rutherford. Okay. So what you should get out of this slide is fillings give you charts inside of this variety, which is called the augmentation variety. I guess I didn't explain why it's a variety, but so you can check from this definition. It's just some sort of affine algebraic variety thing inside of, okay. So once you mod out by homotopy, it's actually some sort of stack, but I'm going to ignore that. So think of this as some sort of affine algebraic variety. Okay. So why am I talking about this augmentation variety? I want to motivate it in a couple of ways. So one of them is that you can really think of the augmentation variety. Well, so firstly, it turns out to be an invariant under Legendrian isotopy. And essentially, that's just because it's spec of the degree 0 linearized contact homology. Legendrian contact homology of lambda. But also because of this correspondence between fillings and augmentations, you can think of this as some sort of algebraic stand-in for the collection of fillings of lambda equipped with rank 1 local systems and maybe up to Hamiltonian isotopy. Okay, so this example that we've been dragging around, this is the trefoil. So the augmentation variety actually looks like this. So that follows from a computation that I wrote down on a previous slide. So this is a variety thing sitting inside of affine 3 space. And Ekholm, Hanna, Coleman show that there are 5 fillings of this trefoil, each giving you a chart of a 2-dimensional torus sitting inside of algebraic torus sitting inside of this augmentation variety. And they're actually, those 5 charts are all distinct, which means that all of these 5 fillings are actually distinct. And they cover the augmentation variety. So I'm going to redraw this in a second, but the augmentation variety somehow looks like a union of 5 things that come from the 5 fillings. Okay. Great. So the reason that I've actually brought up the augmentation variety, so I've tried to motivate it here, but really what I want to do is I want to say, what does this have to do with the Poisson bracket I mentioned earlier? Well, it turns out that it dualizes in this case. So if you think of the augmentation variety as like spec of the Legendrian contact homology, then the Poisson bracket on the Legendrian contact homology then dualizes to a symplectic form on the augmentation variety. So I've tried to give an example of that for the trefoil. And the symplectic form is then invariant under Legendrian isotopy. And the reason for that, so we now call this the Sabloff form. The reason for this is that it is a globalization of something, so a phenomenon called Sabloff duality, which very briefly is just, so if you take the augmentation variety of a Legendrian, so at a point on that augmentation variety, so that is to say at an augmentation, if you look at the tangent space to the variety at that point, that gives what's called linearized Legendrian contact homology. And what Sabloff duality is that it's a non-degenerate skew symmetric pairing on that linearized homology. So that's to say it's just a skew symmetric non-degenerate pairing on this tangent space. And so what we are able to do is to say that, okay, so that's great. So on each tangent space, you have this thing, but in fact, that they glue together globally to give you a two form on the augmentation variety, which is actually closed. And the closedness comes from the fact that the Poisson bracket satisfies the Jacobi identity. Okay, so this is nice. So what this says is that one way to interpret the Poisson bracket that I was describing before is that it gives you a symplectic form on these augmentation varieties. And then the same sort of functoriality conjecture that I wrote down before should still hold here, we hope. And this is that this symplectic form is actually functorial. So if you have a cobordism between two Legendrians that induces a map between the augmentation varieties that now goes from bottom to top. And the conjecture is this is actually a symplectic map. Okay, great. Okay, so that's a little bit about a way to interpret. Oh yeah, so I mentioned this is in, or I didn't mention, but I wrote down here that this is in progress. So we're working on writing this up, and so this well, there will be more results that I'll describe in a second that we're trying to write up. So this is still in progress. So this is a little bit about a geometric interpretation for this L-infinity structure, or at least a piece of it. And then what I want to do for my remaining few minutes is to talk about how this relates to again going to okay, good. So,
Then your screen was frozen for a second.
yeah, I saw that.
I think all is working, and by the way, there is also a quick question in the chat, but otherwise should be good.
Is the implicit statement that the tangent space is the degree 1 part of linearized LCH? So it's actually that it's the degree 0 part of linearized LCH. It's actually so it should be the degree 0 part of linearized Legendrian contact cohomology, and there's some sort of weasel words that I should put in there because again, this is sort of in the nice case where we don't have to mod out by homotopy, but that's at least the motivation. Okay. Great. So it's been known for a while that there's a close connection between symplectic topology and cluster algebras through things like wall crossing formulas. And that's been known for a while, but more recently this has been imported into the study of Legendrian links. And so I just wanted to give you some examples through our running example of how this works. So here's my picture from the previous slide of the augmentation variety of the trefoil, and it's covered by these 5 torus charts corresponding to the 5 fillings. And these charts actually give this augmentation variety the structure of what's called a cluster variety, a cluster A variety. And so what these sorts of things are very loosely, so I'm not going to define a cluster A variety, but you can think of it as being a variety that's covered up to codimension 2 by what are called cluster seeds. So these are exactly these torus charts that I've drawn here, along with some distinguished set of cluster coordinates and also a quiver. And then on overlaps, these cluster seeds, so think of them as just charts. On their overlaps, there's some change of coordinates that also needs to be well behaved, and this is called cluster mutation. So the point is that this augmentation variety for the trefoil actually has a very rigid structure on it that has been studied starting from work of, in this case, Falk and Goncharov. And it turns out that this is not at all unique to the trefoil. So in fact, there are many classes of Legendrian links where the augmentation variety is a cluster A variety. And the one that I want to focus on is this rainbow closures of positive braids. So this is this family that I talked about before. This is a family of Legendrian links that are associated to positive braids. So it was proven that I hope I got these attributions correct, that the augmentation varieties for all of these Legendrian links are actually a cluster A variety. And the geometric, so I find this little stupid little chart here to be helpful. So the only reason I'm calling it stupid is you can make it much more elaborate, but I'm just trying to simplify it very much. So there's some sort of correspondence between the cluster world and the world of augmentations. So I mentioned that an exact Lagrangian filling gives you some sort of torus chart sitting inside of the augmentation variety. So that's that exact Lagrangian fillings give you these cluster seeds. And then if you go from one Lagrangian filling to another one through Polterovich surgery, then this should correspond to this cluster mutation. So that's going from one seed to another, and on their overlaps, that's exactly this cluster mutation. So that's the intuition for this. Right. So okay, great. So a lot of these augmentation varieties, and in particular rainbow closures of positive braids, have this structure of a cluster A variety. And what is nice is that for this family of cluster A varieties, they actually already have a symplectic form on them, which is essentially each of these cluster charts has a canonical symplectic form on it, and then they glue together nicely on overlaps because of this cluster mutation condition. So that's this statement here, that these cluster varieties, so in particular these cluster varieties that come from looking at the augmentation variety for a rainbow closure of a positive braid, these carry some sort of natural symplectic form. By the way, this family of varieties, these augmentation varieties of rainbow closures of positive braids, I think these are called braid varieties in the literature. They've been studied in a number of contexts, like in Lie theory and some other things. And so another thing that we prove in our paper in progress is that for this family of Legendrians, that this cluster symplectic form actually agrees with the Sabloff symplectic form that I described earlier. So this is something. This is actually what sort of motivated us to describe this Sabloff form, was that we knew that for this family of Legendrian links that there was some sort of nice symplectic form. And then the question is, can you extend this to generalize this to other families of Legendrian links? And the answer is yes. And that was sort of what motivated us me to write up the L infinity business. Okay. Amazingly, I have 1 minute left, so I can get to my final slide, which is just some things that we're still working on. So my feeling is that we've only sort of scratched the surface of what is possible even in this setting of just this simple setting of Legendrian links inside of standard context R3. So one thing that I'm pretty excited about is some sort of version of quantization. There's a result that says that, so there are actually two types of cluster varieties. They're called cluster A varieties and cluster X varieties, and they're dual to each other. And for the type of Legendrian link that I mentioned before, which is positive braid rainbow closures, the augmentation variety, this braid variety, actually has both of these structures. And this allows us to construct what's called cluster quantization of these braid varieties. And this actually we can see just completely without talking about clusters at all. And so this is a result that my collaborators, I never actually mention their names, but Roger Casals, Honghao Gao, Linhui Shen, Daping Weng, and in this case, we're joined by Eric Zaslow. What we've used this cluster quantization to motivate is that actually you can take the Legendrian contactology, so the Chicana-Valley-Ashford DG algebra for this family of Legendrian links, and it can actually be quantized. Maybe quantized is not the right word. It can be Q deformed. So you can introduce this parameter Q and deform this DG algebra to an invariant that involves this new parameter q in such a way that the classical limit, so when you just set q equals 1, you get the underlying original DG algebra, but the semi-classical limit, so that the first order information that's in this Q deformation recovers the L2 operation from the L infinity structure. So this is something that we're working out right now. So I don't know whether to call it a theorem or a conjecture. It might depend on exactly how broad we want to be. So I think this actually should hold in much more generality than just rainbow closures of positive braids, maybe for actually all possible Legendrian links if we state it correctly. So this is something that we're working on. And I think I will stop there. Thanks.
Wonderful. Let's thank Lenny for this talk. Any questions? There are some questions in the chat, Lenny. Okay. The one question.
Yes, we can do it. Do we have a geometric intuition for what the cluster analog is for augmentations arising from immersed Lagrangian fillings? Yes, so those also give cluster charts. I don't really understand this so well, but indeed, yeah, even for Legendrian links where there are no embedded exact fillings, you can run some sort of similar picture with immersed fillings as well. You have to be a little bit more careful because now there's this issue of how do the various, so each of these fillings does give you some sort of chart. You can write down some nice coordinates on it, and then the question is what's the notion of cluster mutation? But I think this has been worked out, at least in some families. So this, let's see. So for instance, for this family of Legendrian two-bridge links, which is work of Capuvilla, Searle, and Hughes and Weng, this is a family where in a lot of cases there aren't embedded fillings, but nevertheless they can still show that the augmentation variety, the ungraded augmentation variety, has a cluster structure on it.
Mm-hmm.
Thanks.
Other questions? And to which extent this story is about R3? So can you go other manifolds?
So presumably one can at least do other three-dimensional contact manifolds. At least the story that I've been giving with this L infinity structure, so maybe there's an analog of that for higher dimensional contact manifolds as well, but at least the arguments that I was using with string topology are very three-dimensional specific. So it's an interesting question. I don't know of a very concise answer.
With this story, which includes the bracket, so this L2 operation. So do you have a filtered version? Can you say something interesting about filtered homology? I mean,
filtered by what filtration?
By action.
Oh, by action. Yes. So in fact, all of the operations are filtered. I have not thought about what you can use this for, but that would be an interesting thing to think about.
Mm-hmm. Thank you.
Well, I guess before we move into the discussion, let's thank Lenny for one last time.